we're going to cover today is what a capacitor is, and then what the concept of capacitance is. Capacitors are designed to do something, so we're going to quantify what it is they do. And it's really a kind of defining lesson, you know, just getting you used to the words, getting you used to the quantities and the concepts, and then we'll do stuff with capacitors in the preceding lessons. What I do need to point out for those of you that do electronics is that we're not going to be doing the electronic side of capacitors. So we're not going to be putting them in circuits and seeing what cool things they can do in order to achieve an endpoint the way you would design a circuit in electronics. Really, this is the physics of the capacitor. So what they do, how they do it, how we can make them do it differently. Very much focusing on the theoretical aspect of the capacitor, not very much the practical applications of it. We'll brush against the practical applications, but not to the depth that you do in electronics. Okay, so let's make a start. Okay, so if you do electronics, you will have seen that capacitors are kind of cylindrical objects. They come in all different shapes and sizes. These happen to be fairly big ones physically, but you can get slightly smaller ones as well. They've got two terminals and they're generally cylindrical shaped. Not always, but most of the time cylinder shaped. That's what a capacitor is in electronics, but actually in physics, a capacitor is a much broader item. So if I just hold up a kind of thing that doesn't look like two cylinders at all. So imagine that I've just got two objects that are capable of holding charge. So these are metal spheres. It doesn't really matter that they're spherical shaped. The point is that it's two objects that can hold charge. And I'm just going to imagine what would happen if I plugged them in to the positive and negative sides of a power supply. So if I just draw you a little picture, the negative side of a power supply is the negative side because processes inside the power supply have shunted electrons onto the negative terminal by taking them off the positive terminal. So this side is missing a load of electrons. It's still got all the protons it used to have, but it's missing its electrons, and therefore it's net positive. This side of the terminal of the power supply has received those electrons and now has an excess of electrons, more than it should have. It's still got all its original protons and electrons, but now it's got extra electrons as well. When we connect wires to this, these extra electrons inside here will flood the wire a little bit until there's an even distribution of electrons in the terminal and in the wire. And then on the positive side, when we connect a wire, the free electrons that are in the wire, some of them will be transferred into the positive terminal as they spread themselves out a little bit as well, until the wire and the terminal have an even distribution of positive charge. Now, when I attach these big silvery balls onto the end of the wires, that just gets extended. So I end up with this on here and this on here, and this will be missing its electrons, just like all the rest of this side. And this will have all of the extra electrons. And to that extent, they don't really look much different, the positives and the negatives, do they? Positives and negatives. And we've seen this kind of arrangement before. In fact, I've got a bigger version of this, and if I taught you in year 11, I probably electrocuted you with it. It's called a Graaff Generator. I'm sure whoever taught you in year 11 probably did something similar. So you know full well that this can do groovy things, like if I bring them together, it would spark and things like that. But just in principle, this arrangement would be what we would consider to be a capacitor. And a capacitor is just an object that has stored electrical charge. So this one would have a store of negative charge on it, and this one would have a store of positive charge on it. Now, in this particular arrangement, together they're neutral, but I can even get away with that all on its own as a capacitor, as long as there is something nearby that we can compare the charge to. So this is a couple of meters off the planet Earth, and the planet Earth is a big neutral object that would have fewer electrons than this charged up ball. And therefore, the arrangement of this near to the planet Earth would again count as a capacitor, because this object has more electrons, a greater imbalance of electrons than the planet Earth that's below it. A capacitor really is just an object that has more charge than a nearby object, so that in principle there is the possibility of charge flowing from the place where the charge is to the place where the charge isn't. So you can explicitly have a negative and a positive, or you can just have a negative and a neutral thing, or a positive and a neutral thing. It's beginning to sound a lot like a battery, isn't it, or a chemical cell? But the difference is that in a chemical cell, there is some process going on in here that is maintaining the charge separation. But what I can do with a capacitor is, once it's charged up, I can now connect something in between, like a bulb, and the electrons will flow from the negative place through the bulb to the positive place, just like a chemical cell, and it will light the bulb up, just like plugging it into a chemical cell, but there's no process to maintain the charge, which means that it's like a bucket of water that we're just emptying out with no tap to fill it back up again. So the charge will go through the bulb in a moment, in an instant of time, and then the electrons will run out and there won't be any more electrons. So the bulb will really just flash and then it will go out. So yes, a capacitor has a lot in common with a bulb, with a chemical cell, but fundamentally they are different. They are two terminals with separated charge, but the chemical cell maintains that charge separation, whereas with the capacitor, you have to charge it up and then you have to discharge it, and it's a use once item. You then have to charge it back up again if you want to use it again. It doesn't maintain its charge. So capacitors can be any shape, any size, any separation, but we do tend to tend to settle on a design that is very efficient in terms of space and volume. You can see that this has quite a large volume. It takes up a lot of space. We can achieve the same feat by making the thing a lot smaller with a different geometry. And that's where these cylindry things come up from. So I'm just going to move the camera and we're going to have a little look at what a real, well, the basis of a real capacitor looks like. Let me just move the camera. That'll do. Okay, so you can't see me, but you can see this. So let's have a little look at what we've got. So this is a piece of aluminium foil, just like you've got in your kitchen drawer at home. This is a bin bag, probably in a drawer in your kitchen as well. And then there's another piece of aluminium foil underneath it. So why are we using aluminium foil? Well, we're using the same principle as a thing that's capable of holding charge. So this is a piece of metal. It's quite happy to have lots of free electrons on top of it. It's already got some free electrons at the moment, but in a second, I'm going to attach this lead and we're going to add some extra free electrons to it. And then underneath, this piece of aluminium has got a load of free electrons of its own. And we're going to attach a positive lead to that in a second, and we're going to take some of those electrons off. And so that's going to allow us to have the same arrangement as I just showed you with the spheres, that there will be an object that has an excess of electrons on it and an object that has too few electrons on it. And then we just need to keep the two objects apart. So when I was just holding the spheres, I was holding them apart, but I don't want to be doing that usually. So to package them together, I just need to put something insulating in between them so that the electrons can't travel between the two charged objects. So this is just a bin bag. It's just a piece of plastic because you know that plastic is an insulator. Okay, so let's have a little look at how this is going to work. So I told you I'd put the electrons on the top, so let's do that. And then some on the bottom. Take them off the bottom. Now these wires are actually attached to a 5,000 volt power pack because it actually takes quite a lot of potential difference to move the volume of electrons that I'm about to move. So it's not on at the moment. It's turned to 0. Just in your imagination, do you expect anything to happen when I turn the voltage up? So just have a little think. And here we go. By the way, the camera and the microphone are both sitting very near to the high voltage power supply. It behaved itself yesterday, but in the past, it has interfered with both the camera and the microphone. So if at any point you lose camera feed or you can't hear me anymore, just speak up on the on your own microphone and I will sort it out. Okay, so here we go. So I'm just going to turn it up a little bit. And straight away, we're up to 1500 volts, and you can see the foil moving, hopefully. And hopefully you predicted that. So we're up at about 2,500 volts. And what's happened is that the positive piece of aluminium foil and the negative piece of aluminium foil obviously are attracting each other, and they've just pulled towards each other. So you've kind of had this, it looks like they've sucked together or something like that, like I've just evacuated the air underneath, but it's just attracted itself downwards. Now at the moment, I really have got what would be referred to as a capacitor, in that it is a kind of pair of buckets of charge. I've got a whole load of negative charge on this top piece of aluminium, and I've got a whole load of negative charge on the bottom piece of aluminium. And so this right in front of me on the table is a capacitor. It's a bucket of charge. And I could pull the wires out of the power pack and it would remain charged, and I could attach them to something, and momentarily I'd run a circuit, and we'll be doing something like that in a future lesson. But today I just want to focus on the structure of a capacitor and make sure you understand aspects about it. So I just want to point out one thing while this demonstration is on the table in front of me. It's up at 2,500 volts, and that means that I have put a certain number of electrons on that piece of aluminium. Literally, we could calculate it and write down the actual number of electrons that I've just added to that thing, and maybe we'll do that in a future lesson as well. But I just want you to appreciate that if I made the piece of aluminium foil twice as big, I'd be able to put twice as many electrons on it without changing the setting on the power pack. At the moment, what we've got is that the negative terminal of the power pack has the same electron density as the electrons on the piece of aluminium. If that wasn't the case, if there were more inside the power pack than on the aluminium, then there would be a net force pushing more electrons onto the aluminium sheet. Or if there were more on the aluminium sheet, they'd push themselves back inside the power pack. It's reached an equilibrium. And the power pack at 2,500 volts is maintaining that electron density on the negative terminal. But I can keep the electron density the same by just but have more electrons, by just having more aluminium. The electron density, you know, the number of electrons per centimeter squared, or technically per centimeter cubed, would remain the same. I'd just have more aluminium, so I could have more electrons. So I want you to appreciate that thing, that first of all, that the bigger the aluminium, the more electrons I can fit on, the more charge I can store. And bringing us back to this word capacitance, it comes from capacity. What is its capacity to store electrons? How many electrons can it store, or how much charge can it store? And I need you to appreciate that the bigger the piece of conductor is, the bigger its area, the more I can store on there. But it is a little bit trickier than that. So let me just finish this demo and then I'll dismantle this so that we can have a look at why it's a little bit trickier than that. So let's just ask, well, can I just keep putting electrons on there? So I said that the electron density is matching the electron density on the terminals of the power pack. So let's just increase the electron density on the power pack, and we'll see if I can squeeze as many electrons as I want to onto the aluminium sheet. And for reasons you'll see why in a minute, I'm just going to turn the lights off. Right, so you can't see very much, but that's okay. So I'm just going to turn it up a little bit more. That's 3,500. 4. Okay. That's pretty explosive. So I don't think the camera is picking up the flashes all the time, but you can hear it happening. And you can see on the camera feed that there are some little holes exploding through the aluminium. Okay, I'll turn it off there. Okay, just going to earth that so that I don't get electrocuted. Okay. So what we've got going on there is that there were so many electrons on this top piece and so few electrons on this bottom piece that the attraction between the electrons and the protons on the two different plates was big enough to allow the electrons to actually force their way through the aluminium. And it's actually made tiny little holes in the plastic sheeting. And the electrons have effectively just bored their way through the insulator. And for that reason, we often don't refer to this stuff as an insulator because we might accidentally forget that there's no such thing really as a perfect insulator. Everything is a conductor if you apply a big enough potential difference to it. And so even this bin bag allowed the electrons to conduct when we got up to about 4,500 volts. So we often refer to the insulating material as something called a dielectric. I'll write that on the board in a minute. And that just reminds us that it is going to conduct. Also, we often design and manufacture dielectrics to work particularly effectively. It's not any old material that we just go find like a bin bag. Often dielectrics are highly designed materials. So we will benefit from remembering to call it a different name just to remind ourselves that it's not an insulator. It will conduct at a high enough rate, a high enough potential difference. What that means is that when we're asking about what is the capacitance of a capacitor, yes, the capacity goes up if we make the thing bigger, but it also goes down, or it has a maximum value if the dielectric isn't good enough. So we also need to factor in properties of the dielectric. It's not just about the size of the conducting sheets, by the way, the sheets, when they're flat like this, are often referred to as plates. So this would be the negative plate and the positive plate. Not dinner plates, flat things. So yes, the capacitance goes up if we make the plates bigger, but only up to a limit that is governed by the properties of the dielectric. And also, this topic and the electric fields topic is kind of a chicken and egg thing. You need each to understand the other. So I have to start with one of them. But when we talk about the electric force in the next topic, we will learn that, like gravity, it's distance-based, and the closer together charged objects are, the bigger the force that they experience due to each other. So if these two plates are very, very close together, basically if the dielectric is very, very thin, the force that's attracting the electrons from the negative plate onto the positive plate will be very, very big, and it will be easier for them to tunnel through the dielectric. And therefore, also the separation places a limit on how much charge can be stored on the plates. The closer together the plates are, the smaller the maximum will be, that they won't be able to store as much charge. And then finally, on that note, at the moment, I've constructed these two pieces of aluminium so that the top one is lying on top of the bottom one. Their footprints are the same. But if I were to take this top plate and move it a little bit so that they weren't overlapping fully, so that there was an area here without any overlap, then what we would find is that this positive charge here would have no negative charge above it. And likewise, over on the other side of the capacitor, this negative strip here would have no positive below it to attract it. So if you imagine you're an electron and you're swarming around over here, bumbling about because of thermal motion, then if you happen to find yourself over here, you're going to experience a force attracting you to this positive area that's directly below you. But if you bumble over here, there's no such force to keep you here. And in fact, you'll experience the positive attraction from over here, and you'll flow back again. And so what we find is that if we try to arrange the plates so that they don't overlap, the charge just arranges itself on the overlapping area, and you don't really get much charge on the non-overlapping area. And therefore, it's not as simple to say, what's the area of the conductor? What we actually need to talk about is what's the area of overlap between the two plates. And it's this area here that's actually the important one, not the actual physical area. Okay. That's a little bit about what's often referred to as a parallel plate capacitor. Let's just move the camera back again. Okay. But obviously that parallel plate capacitor is very big, and it's certainly not like that. So all we do, Blue Peter style from yesterday, we just take the parallel plate capacitor and we just roll it up. And so that makes the cylinder shape that you're familiar with. So we could kind of chop the ends of this and take the casing off the outside, and you'd be able to unroll it, and you'd see that it was kind of like a Swiss roll with layers of dielectric and the two plates all rolled up together to make this kind of compact design of a capacitor. But this cylindrical version is really just two flat sheets that have been rolled up together with dielectric between them. Okay, that's talked a little bit about what a capacitor is and what physical aspects of it determine how much charge it can store. But the bottom line is that a capacitor is an object that can store charge. Overall, it's usually neutral, because overall, there's usually two plates and we've taken the charge from one and put it on the other. So overall, it's usually a neutral object, but one end of it is very, very positive. The other end of it is very, very negative. And that means that if we connect it in a circuit, charge will flow from one side to the other side around the external circuit. It's a little bit like a chemical cell. It doesn't have the capacity to recharge itself, but what it does mean is that it's got very, very, very little internal resistance. And therefore, when charge does flow from the capacitor, you can get incredibly high currents, albeit for a very short amount of time. It has other things going for it as well, but capacitors do have that advantage. Okay, I'm going to write something on the board. I'm going to write down, I'll draw a little picture about what a capacitor is, and then we're going to write down a couple of formulae to allow us to calculate how much charge will be stored on the capacitor. And I think that will probably take us through to the end of the lesson today. So we'll see how we go. I'm going to draw a bit of a kind of messy 3D drawing to start off with. So maybe take your time over it, make it look a bit 3D. Use a ruler maybe, but sometimes that helps in different colors if you've got them. Okay, so that's trying to get across to you the idea of two conductors with some insulating material sandwiched between them. Okay, so this is a parallel plate arrangement, but I've just made a note at the top that it doesn't have to be like this. I showed you at the start these two spherically shaped objects. If you went up into space and put a load of electrons on the moon, technically the moon and the Earth would form a capacitor. So it doesn't have to be two parallel conductors at all. Dielectric is spelled like that, D-I-A, dia, dielectric. and that's an insulating material. And then we've got the positively and negatively charged plates. We usually use capital letters to refer to large amounts of something. You remember in gravity, we were using like the capital M for the mass of the sun, and a lowercase m for the mass of the Earth, because the mass of the Earth was so much smaller than the mass of the sun. So we're going to use capital Q to represent the total amount of charge that's stored. And note that the total amount is one lot of Q, because the plus Q here is due to losing the minus Q, which is turned up on the other plate. So we have moved Q lot of charge from one plate to the other. It's only one lot of Q that we've moved. These objects used to be neutral, so this one has become plus Q by losing the Q, the Q lot of electrons, and this one has become minus Q when it gains the Q lot of electrons. Another variable that we're going to be using down here is the charging voltage, or charging PD. We always use traditionally the capital V for that. If you are an electronics student, you might like to just make a note to yourself alongside this sentence that we rolled this up into a cylinder shape when we connect it in circuits. Okay, so I am falling into a kind of lecture style where I'm just speaking at the camera. Do any of you want to unmute and ask me any questions about anything we've done over the last 20 minutes or so? Okay. Is anybody still copying that down? Shall I give you another couple of minutes? Or are you ready for me to move on? Just unmute or...
Still copying it down.
Still copying it down. Okay. Give me a shout when you're ready.
Sir, I think dielectric is spelled D-I-E-L-E.
Is it? You know, I've been spelling it with an A for years.
Okay, well, I just checked both the textbooks and they both spell it with an E.
Oh, well, let's go with an E now. I stand corrected. Makes more sense, I guess, dielectric.
Yeah.
I'll even do it in another color to make it stand out. Wow, seriously, years I've been spelling it with an A.
Okay, I've copied it down.
Thank you very much. Anybody else? We good?
I'm good.
Okay, it's been recorded as well, so if you need to, you can play it back later. And hit pause. Okay, so question we now want to ask, which is going to be the most important question for the physics of the capacitor, the way that we're going to work, is how much charge can we store on that thing? What is its capacity? So what we are going to do is just define it. It's our variable. We can choose to make it whatever we want. So we're going to choose to do it in a way that makes sense and is useful to us in the future. And we're going to take a similar approach to the way we've defined lots of things in the past. We know full well that electrons will flow onto the plates of the capacitor because of this charging potential difference. But that's after we've designed and made it. So all of these capacitors that I've got here, they'll all hold Q lots of charge, but they're all slightly different designs. They're all slightly different sizes, slightly different dielectrics, surface areas, separations of the plates inside the coiling. So they've all got slightly different designs, which means that some of them will store electrons more easily than others will. But I can store Q lots of charge on any of them if I just set the charging PD to the right value for each one. And therefore, we need to, in our head, accept that there needs to be a division between the manufactured object and the amount of charge that's actually on it, because that will vary depending on the potential difference. So if we want to ask about the capacitor of this independently of what we've attached it to, we need to take this out of the picture. And we just need to agree that we'll use a value at a set potential difference, just so that we can compare them between them. It's a little bit like when we define density. We just said it was going to be the mass per unit volume because it was just an arbitrary choice, but we liked the number 1 because it made all our sums nice and easy. So we're going to do a similar thing now, and we're going to say, if I give you a capacitor and you don't know what its capacitance is, then what you just need to do is just attach it to 1 volt. Just attach it to a power pack at 1 volt and then test how much charge is on it. And however much charge is on it at 1 volt, we're going to call that the capacitance. Now, that might not be the maximum amount of charge that this object can hold, so it's slightly misleading. Capacitance makes it sound like the capacity of a bucket. It might be a 10-litre bucket because you can fit 10 litres into it. And it'll still be a 10-litre bucket even if you put 1 litre into it. That's not how we're using the word capacity here. What we're really talking about is the amount of charge at 1 volt. That's going to be however much charge is in it at 1 volt. We're going to call that the capacitance. And then the actual capacity, the maximum charge that it can store, might be a lot higher than that if we apply more than 1 volt to it. So capacitance rather than capacity. So the capacitance is going to be defined as the amount of charge that is stored, capacitance, the amount of charge stored per unit PD. And this is one of those textbook definitions where, you know, question 4, part A, part 1 says define capacitance, and you write that. The amount of charge stored per unit PD. Please don't write anything else. In particular, please don't write per unit volt. It would be volts in SI units, and yes, we do usually use SI units, but we don't have to use SI units. So please write definitions of quantities in terms of quantities. So capacitance is a quantity, define it in terms of charge, which is a quantity, and PD, which is a quantity.
Sir?
Yeah.
What is the definition of dielectric? Like, would you have to know that for an exam?
No, you wouldn't. You just need to know that it is the insulating material that's between the two plates.
Okay.
By the way, on the subject of dielectrics, seeing as you asked, they are manufactured materials, and they are often, it's often the case, mostly the case, that in order to give them as the maximum insulation properties that they can, it turns out that materials can be, molecules in the material can be arranged and manufactured in such a way that it can have an incredibly high, it can have a much higher insulating effect as long as you force the electrons to travel across it in a particular direction, the hardest direction. So when capacitors are made, when the dielectric is put inside them, it's often orientated in such a way that the molecules are lined up in the direction that prevents maximally the flow of electrons. What this accidentally means, though, is if you allow the electrons to flow in any other direction, it's just not very good at insulating at all. And in particular, if you muddle up the terminals on the outside, if you accidentally attach the negative wire to the positive terminal, then the thing has been designed to stop electrons from traveling in one direction. It hasn't been designed to stop them traveling in the other direction. And if you accidentally wire it up the wrong way, electrons really will flow straight across the dielectric as if it's not even there. And you'll get a very, very, very large current inside the capacitor, which will have a heating effect on the dielectric. And it will first melt it, and then it'll vaporize it. And then as the liquid turns into a gas, it will expand very quickly. And capacitors are in metal boxes, sealed metal boxes. And so they tend to explode. And you get molten dielectric flying out at you, which is often toxic. So if you were in school right now, I would be being ever so slightly neurotic about getting you to wire up your circuits the right way round so that you didn't have any capacitors popping in your faces. But you're not here, so there's one bonus, right? You can't explode the capacitor in your face by accidentally wiring it up the wrong way. Okay, so we can turn that into a formula. So capacitance, which we use a capital C for. So those of you back in year 10 and 11 who were really upset that we weren't using C for current, that we had to put up with I, well, here's why. Because C got nabbed for capacitance long ago. So the capacitance is equal to the charge stored per unit of PD. So if you don't happen to have one lot of PD, you're going to have to scale it. So say you've got 20 coulombs stored for 2 volts. Well, that would mean that you would only get 10 coulombs for 1 volt. And that's why we divide by the potential difference to just scale it to 1 volt if you don't happen to have used 1 volt when you did your charge measurement. So that's your go-to formula, although, to be honest, we do usually know what the capacitance is because it's printed on the side of the capacitor, and we do usually know what the potential difference is because we've done it ourselves and we've attached a voltmeter, or we know what the power pack's set to. So actually, we usually know what C and V is, and usually what we're trying to do is work out how much charge is stored. So that formula is actually more usefully written as Q equals CV, and that's the form that you'll be using it in calculations the most often. But this is the defining formula, so I'll give it you the right way round, but that's the more useful expression of it. Okay, units. So charge is in coulombs, potential difference is in volts, and that means that capacitance is in coulombs per volt if we're using SI units. However, you know how this game is played by now. Someone devotes their life to studying something, and then when they die, they're not given a statue, but they're given a unit. So the person who studied capacitance a lot was called, anybody happen to know?
I know his surname, Farad.
Oh, Farad, yeah. So we actually call these farads, capital F. Just a note about farads, or indeed the coulomb per volt. You remember perhaps that the unit, the coulomb, is just silly big. You remember that there's like 6 billion electrons in a single coulomb. So because the Coulomb is so very, very big, you are highly unlikely to manage to store an entire Coulomb on a tiny little capacitor by applying just a single volt. That is very, very, very unlikely. Capacitors that can do that are generally the size of pedal bins. So for these tiny little things, they can't store anywhere near an entire Coulomb if you attach them to just a single volt. So you are never going to meet a capacitor that has a capacitance of 1 farad. They're always microfarads, millifarads at best. So yeah, the farad is a stupidly big unit to go with the stupidly big Coulomb. Microfarads or millifarads usually. Okay, so if I give you a capacitor and maybe the markings have rubbed off and you want to know what the capacitance is, one way of working it out would be to apply 1 volt to it and then attach a Coulomb meter to it and ask how much charge is stored. Or actually, Coulomb meters are quite difficult. We'll find out over the next few lessons how we can measure it by various means. But this is, in principle, a method. You could charge it to 1 Coulomb and then see how much charge is stored on it. And that will give you the capacitance. But what if you haven't made it yet? What if I'm a customer and you're a capacitor manufacturer and I come to you and I say, I would like a capacitor made for me, please, that has a capacitance of 17.3 microfarads. And now you're not going to have one of those sitting on a shelf in a warehouse ready to go. You're going to have to design it and make it for me. So this is a perfectly good formula if the capacitor already exists. But if you're actually designing the capacitor and you want to make it to have a certain capacitance, then that gives us a second formula that's based upon the properties that we've already spoken about. So the capacitor will be bigger if it has got a large overlapping area between the plates. So area is definitely a factor. And we would expect that if we double the area, we can fit twice as many electrons on it because there's twice as much space for them to exist in. Likewise, the closer the plates are together, the bigger the force between the electrons, allowing them to have a greater opportunity to tunnel through the dielectric and not remain stored on the plates. So having the plates close together reduces the capacitance. Now, it's not going to be clear to you why it's inversely proportional to D. The D goes on the bottom, but why it's D and not D squared or D cubed or D to the 1.2, we need to study electric fields a little bit more to make that a little bit clearer. So for now, you're just going to have to accept that it's to the power 1, and we'll come back to that. And then also locked up in here, we need to have something about the dielectric. Its insulating properties, basically, how good it is at preventing the electron flowing. But it's not really resistance as in V equals IR, because that's a definition of resistance when there is a current flowing. But the dielectric's entire job is to prevent a current flowing. So it's not quite as simple as resistance, but it's that kind of concept by how insulating is it, how good is it at preventing electrons from flowing through it at all. So the word that we use for that, and on your particular A-level specification, we don't dwell on it very much as a concept, but I am going to mention it. It's called the permittivity. Kind of like permission. Does it allow the electrons to flow or not? I find the word to be not particularly useful or intuitive, and I just focus on the fact that it's the Greek letter epsilon. And then we've got this constant of proportionality here, but it turns out that if we just pick our units of this carefully enough, we can make sure that the constant is 1 and that this is just our formula. So if you happen to already own the capacitor and you just want to plug it into a circuit and find out what its capacitance is, you would do this formula. But if you're designing the capacitor so that it has a particular value of capacitance, you would make sure that you tweaked these three values appropriately so that you can achieve the value that you want in the scale form that you want, so that it also fits on the circuit board, I guess. Can I just mention this as a final thing before I finish? It's actually equal to something called epsilon naught, which is the permittivity of a vacuum, no matter at all. And then what we do for all of the other materials is just express their permittivity as multiples of the vacuum permittivity. It's almost like we use the unit of the vacuum permittivity. So the bin bag might have a permittivity of 3 lots of vacuum permittivity. It just allows us to tabulate the values a little bit easier and compare them a little bit easier. So this is the vacuum permittivity. And this is then a scale factor called the relative permittivity. Okay, that's what I wanted to get through today. I wanted you to see what a capacitor was, and I wanted you to have the definition and the formulae for calculating it. I'm going to leave you with some questions to do to practice using those two formulae and the definition. And then next week, when we pick this back up again, we're going to have a look at the physics of a capacitor. Not so much, like I said, how we would use a capacitor in a circuit, a little bit, but not much. More the physical properties of a capacitor and what it's capable of doing.